Good evening, everyone. Am I audible?
Good evening, ma'am. Yes, you're audible.
Okay. So we'll continue with the exercise problems. If you have any doubt related to the previous session, you can ask, or else I'll move forward. Okay. In the previous session, we discussed some problems related to matrix spaces. We proved some matrices on different spaces. Saw the how the convergence happens in a different kind of spaces. Let's continue with the exercise problems that were left during the lectures. So let's start with question number 1 for today. Prove that any intersection of closed sets is closed and a finite union of closed sets is closed. So can anyone tell me the definition of closed sets, or basically what do we need to prove in this question?
Closed set contains each adherent points.
So basically the points that belongs to the set union the set of limit points. So if the first part of the question says that prove that any intersection of closed set is closed. So if I take a collection, let a lambda belonging to capital lambda be any indexing set. This indexing set can have uncountable number of elements as well. Be a collection of closed sets. Let A be the intersection of all these sets. Lambda belongs to lambda, A lambda. We claim that this set A is also closed. So obviously the members are already in this set. All we need to show is that all of its limit points are in A itself. That means if xn is a sequence in A such that it converges to some x, that means this x is a limit point. We need to show that this x belongs to A as well. That means A contains all of its limit points and hence it is closed. Is it clear why we are proving this in order to show that the set is closed?
Yes, ma'am.
Okay. Now, since xn belongs to A, xn belongs to A for every n in n, and this A was actually the intersection of A lambdas, that means xn belongs to A lambda for every lambda in lambda and n in n. That means xn is a sequence. This implies xn is a sequence in A lambda and xn converges to x. Now, since this is happening for every lambda in lambda, now since A lambda is closed set, this implies it has all of its limit points. That means x belongs to A lambda for every lambda in lambda. Why? Because A lambda is closed and hence contains all of its limit points. Limit points. Now this implies, now since x belongs to A lambda for every lambda, that means x belongs to the intersection as well, which is A. Now since x was an arbitrary limit point of A, we can clearly see that A is closed. Therefore, A is closed. And hence, any intersection of closed sets is always closed. So can you try the union part? Just try it yourself. Suppose we have finitely many closed sets B1, B2 up to Bn, and we take B to be union of all those Bi's. Then we need to show that this union is closed. So all you need to use is the fact that the complement of closed set is open. So basically we have a finite collection of closed sets. Let B1, B2, and so on up to Bn be closed sets, and B is union of all these Bi's. We claim that this B is closed, or B complement is open. Obviously, we all know that complement of a closed set is open. Now we have B complement. This is complement of union I from 1 to n Bi, and we know that this is equal to intersection I from 1 to n Bi complement. Now since each Bi is closed, that means Bi complement is open, and we know that finite intersection of open sets is again an open set. Therefore, B complement is open. Since Bi is closed for every I on 2 up to n, this implies Bi complement is open for every I. This implies intersection I from 1 to n Bi complement is open. Why? Because finite intersection of open sets is again open. And this is equal to B complement. B complement is open, and hence B is closed. I hope this is clear.
Yes, ma'am.
So this is a very important point you should remember, that arbitrary intersection and finite union of closed sets is closed. Okay, let's move to next question. Let f from x to y, where x and y are two matrix spaces, be a mapping between matrix spaces with the property that whenever xn is convergent in X, the sequence f of xn is convergent in Y. That means every convergent sequence is mapped to a convergent sequence. Show that f is continuous. So we all know, yes, Mayank, nahin, MD Shakil. So you have a doubt?
Yes, ma'am. Ma'am, can we have an infinite union of closed set which is not closed?
Infinite union of closed sets. Yes,
Yes.
you can find. Try to look for some example. There exists such example. For hint, I can tell you that consider the space R, set of real numbers, and look for some closed sets. You can find some type of closed sets whose arbitrary union, infinite union, will give you an open set. Try it yourself. This would be a good
Ma'am.
exercise.
Okay, ma'am. Thank you.
So let's recall the sequential criteria of continuity. We know that. We have f, suppose f is a function from x to y. We say that f is continuous if for each sequence xn converging to x, we have fxn converging to fx. So using this, we'll show that the function f is continuous. So we are given that whenever xn is convergent, suppose xn is converging to x, we know that this sequence fxn is convergent. All we need to show is that the limit is actually fx. That's what the main part left here is. So suppose xn is some sequence that converges to x in capital X by the given property of f, property of f, we know that fxn is convergent. Suppose this fxn converges to some y in y. So we claim that we claim that this y is actually f of x, and hence by sequential criteria, the function f is continuous. Now, if I consider the sequence, consider a new sequence yn, which is equal to x at even positions. That means whenever n is equal to 2, 4, 6, 8, so on, or I'll write it as n is equal to 2k, k belonging to n, and I define yn to be equal to xk, where n is equal to 2k minus 1, or you can write that k is equal to n plus 1 by 2. So can you see the elements of the sequence yn sequence? How will it look like? Its first term will be, so when n is equal to 1, that means n is odd. So by the definition, this yn will be equal to xk, where k is n plus 1 by 2. That means 1. When n is equal to 1, k is equal to 1. So this is just x1. Then second term, by definition, from here, second term will be x. Next, you can see that y3, from here, it will turn out to be x2. Then again x, then x3, x4, and so on. Something like this. So can you tell me what will be the limit of the sequence? This yn will converge to, use the fact that xn is converging to x.
It will converge to x
How?
because xn also goes to x, and the even uh, term is also
So the
fixed.
complementary subsequences, both the complementary subsequences, y2n and y2n minus 1 are converging to x. Hence, the sequence converges to x. This implies yn converges to x. Now, since yn is convergent, again by the property of fyn is convergent. Convergent in y. So we know that the complementary subsequences of a convergent sequence converge to the same limit. In fact, any subsequence of a convergent sequence converges to the same limit. That means fy2n and fy2n minus 1 converges to same limit. This implies limit n tending to infinity fy2n is equal to limit n tending to infinity fy2n minus 1. Now this y2n minus 1 is basically xk. So this is limit n tending to infinity fxk, and y2n, this is limit n tending to infinity fx, because all the even terms are equal to x. Now this is a constant sequence. This implies fx is equal to limit n tending to infinity. Sorry, from here, from this next step, this term, this is converted to xk. limit k tending to infinity fxk, and we know that this is equal to y. That's how we started. Therefore, y is equal to fx. That's what we need to prove, and hence since x belonging to x is arbitrary, hence f is continuous on x. I hope this proof is fine with everyone. So the main thing that we needed to show that this sequence fxn, this convergent sequence fxn is converging actually to the point fx. For that, we constructed a new sequence and used the given property of the function f. Okay, then let's move to the next question. Question number 3. Show that a mapping f from x to y between matrix spaces is continuous if and only if the image of any closed set is closed. I hope you all must have gone through the lecture videos. There we have already proved that f is continuous if and only if the pre-image of an open set is open. That means f inverse g is open in X for every open set G in Y. This is a characterization of continuous functions. So we will be using this characterization and the fact that the complement of closed set is open in order to prove this statement. Solution. Now let F be a closed set in Y. F be we'll start with suppose F is continuous. Suppose F is continuous. Now we need to show that the image of any closed set is closed. So let F, capital F, be a closed set in Y. This implies F complement is open in Y And since F is continuous, this implies F inverse F complement is open in Y, open in X, since F small f is continuous. From here, I'm saying that this implies F inverse F whole complement is open in X. This I'm saying because this you can prove that F inverse capital F complement is actually equal to the complement of F inverse F. So in order to prove this, you can start with X belonging to F inverse capital F complement. This implies and implied by Fx belongs to F complement. This happens if and only if Fx does not belong to capital F. This happens if and only if X does not belong to F inverse of capital F. That means X belongs to F inverse capital F complement. And hence these sets are equal. So is it clear how these two sets are equal? And from here we directly get F inverse F is closed in X. Hence, if F is continuous, then pre-image of any closed set in Y is closed in X. Please go through this proof. Converse part is a bit easier. Again, we'll be using the characterization of continuity. Conversely, suppose pre-image of any closed set is closed in X, then in order to show that F is continuous, we'll be showing that pre-image of any open set is open. So suppose, let's start with the I'll write in detail. Suppose pre-image of any closed set in Y is closed in X. And we claim that F is continuous. So in order to show that this is continuous, we'll be using the characterization. Let A be an open set in Y. This implies A complement is closed in Y. This implies by the hypothesis A F inverse of A complement is closed in X, and again similar to as done in the previous part, this is equal to F inverse A ka whole complement is closed in X, and since complement of closed set is open, this implies F inverse A is open in X, and hence Since the preimage of an open set is open in X, we'll get F is continuous on X. I hope this is fine.
Yes, ma'am.
Okay, then let's move to next question. Question number 4. Let X be the collection of all bounded linear maps. Consider X to be LEF, which is collection of bounded linear maps. By bounded linear maps, we mean the maps which are continuous and linear between the normed spaces E and F. Then define norm is equal to infimum. Now, since for in every function f in LEF, we know that it is continuous as well as bounded. Then, if you remember, in that case, we know that there exists some alpha positive such that f norm fx, this is in the norm of f, this is less than equal to alpha times norm x. So we have such a relation in case for every bounded linear function. Now we'll be taking infimum of all those alphas possible. Infimum C positive norm Tx is less than, sorry, this is L. I'll write this as T is less than equal to C times norm X for every Ln, for every T in X. So that this forms a norm. We This is indeed a form, indeed a norm, and we call it the operator norm. Forms a norm, and it is called the operator norm. So in order to prove that this is a norm, we need to prove the 4 properties. The first one is recall. We need to show this forms a norm on some space X if first one, this is positive. Second one, this is equal to 0. If and only if X is 0, then the scalar multiplication, this is equal to mod alpha times norm X. And last one is the triangles inequality. So we need to prove these 4 properties. So clearly first one directly it is, since it is positive, clearly norm T, this is equal to, since we are taking infimum of all overall strictly positive real numbers, such that it is x for every x in for every x in E. This is positive. Next is we need to show that this is 0 if and only if t is equal to 0. Clearly, if t is equal to 0, directly 0 is equal to norm tx. This is less than equal to c norm x for every c positive. So eventually this infimum will be equal to, so this had nothing to do. Okay, so norm t is equal to 0. Next, conversely, suppose the infimum is positive norm tx less than equal to c norm x. This is equal to 0. Now we'll use a property of infimum. If you remember, suppose alpha is infimum over a set A, then for any epsilon positive, there exists some A epsilon in A such that the infimum plus epsilon is strictly greater than this A epsilon. I hope you remember this property of infimum. So from here, now since this infimum is 0 in our case, this implies for epsilon positive, there exists some C epsilon positive such that 0 plus epsilon is strictly greater than C epsilon, and the C epsilon belongs to this set. That means norm Tx is less than equal to C epsilon norm x for every x in E. Now this implies norm Tx. Now since C epsilon is strictly less than epsilon, from here this is less than equal to epsilon times norm x for every x in E, or in fact this is strictly less than. This implies norm Tx by norm x, this is strictly less than epsilon for every x in E minus 0, because we cannot divide by 0. So I hope you all are clear that when we are taking this norm over Tx, this is the norm of F, and when we are taking norm over x, this is the norm of E. Now from here, we get norm Tx by norm x is strictly less than epsilon for every x in E minus 0. And since epsilon positive is arbitrary, we get norm Tx by norm x is equal to 0 for every x in E minus 0. And since t is linear, so t of 0 is 0. So this implies norm Tx is equal to 0 for every x in E, because obviously t is linear. So t of 0 norm is basically norm 0, which is again 0. And for rest of the part from here, we get norm Tx is equal to 0. And since this is a norm, this implies Tx is equal to 0 for every x in E, and hence this t is actually the 0 operator. So therefore, this norm t is equal to 0 if and only if t is 0. So we are done with property 3, property 1 and 2. Property 3 is a bit straightforward. So the third one, let alpha belongs to the field So whatever the field was, be a scalar. So that depends on the field of vector space E and F. So, Shakil, is this hand raise was the earlier one,
Yes,
or okay, okay.
ma'am, in the converse part of property number 2, where
Hmm.
in one step, that is norm of tx is strictly less than epsilon times norm of x.
Hmm. Hmm.
True, all x belongs to E. But in the next step, x is from E minus 0. But
Yes, because we cannot divide by zero, na?
yes,
So
but
that is why while here while taking whole space E, I have told that for zero the term this comes directly from the fact that T is a linear map.
oh, okay, that is defined in different case. Okay.
Yes. See, E minus zero is eventually a subset of E. If something is happening on E, then it should happen on the subset also. So this is fine. From here, we get this for all x belonging to E minus 0. Now we need to check what happens at x equals to 0. Now since t is linear, so at x equals to 0, we know that for linear map, 0 is mapped to 0. So from here, t of 0 is also 0. And hence
Okay,
we
okay.
got for all x. Okay. Next, let alpha be a scalar. Then from here, alpha t, this is infimum over all c positive, such that alpha tx, this is less than equal to c times norm x for every x and x. Now since this is a norm, this is equal to infimum c positive, I can take this alpha mod alpha outside. Norm tx less than equal to c times norm x, and this is equal to, so let's start with alpha non-zero. So I can divide by mod alpha, say by mod alpha times log x for every x and x. Sorry, not x, this is e. So I can write this as infimum over mod alpha times k positive norm dx less than equal to k times norm x. I have just replaced c by alpha by k. So from there we get c to be equal to mod alpha times k for every x in e. Take care.
Ma'am,
Yes.
here also alpha cannot be 0, isn't it?
Ah,
So
I've
when we
started with the case alpha non-zero.
oh, okay, okay, thank you.
While dividing, we should always take care of this fact. We cannot divide by zero. So this is, from here I can take this alpha outside because it is independent of the things happening inside. Infimum k positive norm tx less than equal to k norm x for every x and e. Now this is the definition of norm over f, norm over t. So from here we get norm alpha t is less than equal to mod alpha times, this was mod norm t for every alpha non-zero. And what happens for the case alpha equals to 0? For alpha equals to 0, alpha t is 0. So its norm will be 0. We had seen earlier in part 2. So I can write this as 0 times. So from here, mod alpha t at any point x, this is nothing but 0. And I can write it as 0 times. Sorry. So this should be. This is non-zero. And I can write it as norm t. So which is basically mod alpha times norm t. Hence, norm alpha t is equal to this is equal to mod alpha times norm t. Next, we need to prove the triangles inequality. I hope till here it's fine.
So, ma'am, here the norm of alpha into t will always be equal to norm of mod of alpha into norm of t. Can it be strictly less than?
No. It will be equal because this you can prove yourself also. If you take a set A and another set, some scalar multiplication by a positive number, you can see that infimum of alpha A will be equal to, yeah, this is something of the form mod alpha A. This will be equal to mod alpha times infimum of A. Try using this definition of infimum. You can prove this fact.
Okay, ma'am, thank you.
Okay, next we have the triangles inequality. So let P and G be some linear maps, bounded linear map. Then by definition, now T plus G, this is equal to infimum of all those C positive such that norm T plus G over X is less than equal to C times norm X for every X in E. And we claim that this is less than equal to norm T plus norm G. So let's start with non-zero X and C positive be such that it belongs to the set. I'll denote the set by S. So let's take this C belonging to S. So that means norm Tx plus Gx, this is less than equal to C times norm X. And since I have taken non-zero X, so I can write it as norm X, this is less than equal to C. So now let's use the triangles inequality of the bound. So this was not used. Let it be. Okay. Now, since F is a non-linear space, we have norm Tx and Gx. This is the norm of F upon norm X. This is less than equal to norm Tx, norm Gx by norm X, norm X for every X non-zero. This is by the triangles inequality. So taking supremum on both the sides, sorry, infimum on both the sides. Uh-huh. This is supremum. Supremum norm Tx plus Gx by norm X, X non-zero This is less than equal to supremum over norm Tx by x plus norm Gx by x. X belongs to A minus 0. Now, if I consider the set A to be the collection norm Tx by x, x belonging to E minus 0, and B to be norm Gx by norm x, x belonging to E minus 0. We know that supremum, yeah, this is also a good exercise. You can try. Supremum of A plus B will be equal to supremum A plus supremum B. Again, using the epsilon definition of supremum, you can show this. From here, you'll get supremum over Tx by x, x belonging to E minus 0, plus supremum of norm Gx by x, x belonging to E minus 0. And I'm saying that this is actually equal to the definition of norm that we had given earlier. So I'd like you to try this yourself, that this is equivalent to saying that infimum of C positive such that norm Tx is less than equal to C times norm x for every x in E. So these two are equivalent. Therefore, norm T plus G, this is less than equal to norm T plus norm G. So it seems like in your tutorial also you have a lot of exercises, but still I hope a lot of things are clear now. These are basic definitions or the properties of infimum supremum that you should be familiar with. That's why I'm leaving this for your practice. So therefore, by above four properties, we show that this is indeed a norm. In fact, it has a way, two, three more equivalent forms that you must have seen in the class. Yes.
Ma'am, we are adding T and G. Is it due to the property that L of EF is a vector space?
Which step?
We can add that is T plus G.
Yeah, addition. We are
Yes.
able to do addition because this is a vector space. Yes. So here
Okay.
actually we have defined T plus Gx as Tx plus Gx. Now since Tx and Gx are two elements in F, and F was the non-linear space, that means a vector space. In vector space we have the notion of addition.
Yes, ma'am. Thank you.
Hence this forms a norm called the operator. Okay, let's move to next question. Then we discussed the equivalent matrices. So this is question number 5. Let X be a matrix space with matrix D, define D dash xy is equal to dxy upon 1 plus dxy. So that this D dash is also a metric on D on X. So that D dash is also, yes,
Ma'am, in the operator norm, there is a property that norm of composition of two operators is less than equal to product of their individual norm. How can we
Mhm.
prove?
So you start with the definition and use the fact of the supremum. Okay, I haven't proved it in detail. I'll prove this one in next class. Okay. Till then, you try it yourself. So I think you'll have to use the definition, the above equivalent definitions. Either one you can use in order to prove this.
Okay, ma'am. Thank you.
X and furthermore, it is equivalent to. So by equivalent, we mean topologically equivalent. So in basically we need to show is that if a set is open in with respect to the matrix D, that means if A is open in XD, we need to show that it will be open in XD prime, XD dash also, and conversely as well. So let's start with proving that this is a matrix. So yeah, someone was telling that for in order to prove that it is a matrix, we need just the three properties. So initially, actually, when we started with the function over x cross x to r plus, so that first property was basic in the definition itself, na? So that can be omitted. Let's start. So clearly, this t prime is a map from x cross x to r plus. So that's done. First, we need to show that this is 0 if and only if x is equal to y. This
Ma'am,
happens if, yes.
actually, in the detail note of sir that he provided us,
Hmm.
in that he mentioned that using the three property we can prove that it satisfies the greater than equal to property.
Yeah, that was also an exercise problem. Huh? Did you try it?
Yes, ma'am, I tried it by putting y is equal to x.
Okay.
Then I get inequality.
So you put y equals to x in which of the property?
In the triangle inequality property that he
Okay.
mentioned,
So we had dxy less than equal to dxz plus
plus
dyz. So you put x equals to y. From there you get
dx.
dxx less than equal to dxz plus dxz.
Yes,
So from here this is 2 dxz. Yeah, from here you get dxz is greater than equal to dxx by 2. And from here,
dxx is 0
how is dxx 0? Okay,
because in
yeah, because it is equal. Mm. So this is equal to 0. So eventually, now since this z was also arbitrary, no? So we can write
yeah,
this as for every x, z, and x. Yeah, good. This is a nice way of proving this. So I think one of the assignment problem was also related to this statement. No? If we remove one of the,
Yes,
can we remove one of the properties, something like that.
yes. And that question also it is asked that does modulus of metric is also metric?
Okay. So actually, the metric is already a positive function now. So its modulus will be itself.
Yes. It is tree where it
Ah,
become the
it is true. From here, since this denominator, we can remove this, we'll get dxy is equal to 0. And since D is already a metric, this happens if and only if x is equal to y. So from here, we get the first property. Second one, d dash xy. Yeah, the symmetry partner. So since D is already a metric, it satisfies the symmetry property. So this is equal to d dash by x. So did you try the triangles inequality for this problem? So let x, y, z be three elements in X. We claim that dxy is less than equal to dxz plus dz. So for this, we can start with the fact that the function, consider ft equal to t by 1 plus t. So we know that this function is increasing because its derivative will turn out to be 1 upon 1 plus t whole square. This is always positive for every t in R. This implies f is an increasing function. And since D is a metric, we know that dxy is less than equal to dxz plus dzy. Now, since this f is increasing, so this inequality remains same. F dxy, this is less than equal to f dxz plus dz. So by the definition of the function, this is equal to dxy upon 1 plus dxy. This is less than equal to dxz plus dzy upon 1 plus dxz plus dzy. Now I can split it dxz upon 1 plus dxz plus dzy plus dzy plus dxz plus dzy. Now, since 1 plus dxz plus dzy is greater than equal to 1 plus dxz, so its reciprocal will be less than equal to. So this is less than equal to dxz upon 1 plus dxz. And similarly, since 1 plus dzy is less than equal to 1 plus dxz plus dzy, so its reciprocal will be less than equal to. So this is 1 plus dxz plus dzy. Sorry. Since dxz and dzy, these are less than equal to 1 plus dxz plus dzy. And this is d dash xz plus d dash zy. Therefore, from here we get the triangles inequality. Therefore, d dash xy, this is less than equal to d dash xz plus d dash zy. I hope this is clear.
Yes, ma'am. It's clear.
So next we need to show that both the matrices are equivalent. So by equivalence, we mean that both have same open sets. Next, we need to show D and D prime are equivalent. That means they generate the same topology. So suppose A subset of X be open in XT. So we'll show that this will be open in XD dash as well. Now, since it is open, that means each of its member is an interior point. That means for every x in A, there exists some Rx positive such that x belongs to the ball with respect to the matrix D around x with radius Rx, and this will be contained in A. So by ball, we mean set of all those y in A such that dxy is strictly less than Rx. This set is contained in A. Now, we need to show that there exists some Rx dash. We need to show that there exists some Rx dash positive such that x belongs to the ball with respect to the matrix D dash around x with radius Rx prime, and this is contained in A. Now, I'm taking Rx prime to be equal to Rx upon 1 by Rx. I want you to figure out yourself why I took this. So now if y belongs to the ball with respect to matrix D dash around x with radius Rx dash, where Rx dash is given here, this implies the distance between x and y D dash, this is strictly less than Rx dash. That means dxy upon 1 plus dxy, this is strictly less than Rx prime, which is equal to Rx upon 1 plus Rx. So from here, since everything is positive, I can just cross multiply. From here, I'll get dxy times 1 plus Rx is strictly less than Rx 1 plus dx. From here, so Rx dxy gets cancelled out from both the sides. We are left with dxy strictly less than Rx. So now I think now it's clear why I took Rx dash in such a way, so that eventually I get dxy less than Rx. dxy less than Rx means y belongs to the ball around x with radius Rx, and this ball is with respect to the matrix D. That means y belongs to BD XRX. Now this we know that is contained in X. Sorry, A. So we started with a Y in this ball. We got that this Y belongs to the set A. That means BT prime XRX prime. This is contained in A. Or obviously the center of the ball is always contained in the ball. X prime is contained in. Hence, since X belonging to A is arbitrary, we get A is open in X D dash. I hope this is fine. How we got that A is open with respect to the matrix D prime as well.
Ma'am, what is the intuitive idea of getting the value of Rx prime in such a way?
So while doing the rough work, you can start with the fact that what you want eventually that this, for if I take y in BD prime x with some radius, suppose r. So I want to end up with the fact that dxy is less than r. That's what I want. So because I know that this ball BDRX is contained in A. From here only I would be able to get that this BD prime will be in A. That's what I need. So now this dxy,
Here both R are same or different?
see this is Rx and this is Rx prime. This is just a rough work. So you should start with some Rx so that eventually you get this dxy less than Rx. This Rx was with respect to the matrix D. And you need to take Rx prime such that you get dxy less than Rx. So eventually you need to do all these calculations backward in rough and then start with in the opposite direction.
Okay, ma'am.
Okay, conversely also you can try. Conversely, let A is open in XD prime. That means for every X in A, there exists some Rx prime positive such that the ball with respect to matrix D dash around the point X with radius Rx prime is contained in A. And we need to show that there exists some Rx positive such that X belongs to the ball with respect to the matrix D centered at X with radius Rx is contained in A. In order to show that A is open with respect to the matrix D as well. So Now case 1, you can see that this d prime xy, this is equal to dxy upon 1 plus dxy is always less than or equal to 1. Now if I take this rx prime to be strictly greater than 1, so in that case bd prime xrx prime, this is set of all those points y in x such that the distance between x and y is less than rx prime. Now this rx prime is greater than 1. We know that any 2 points, the distance between the d prime distance between any 2 points is always less than 1. And we want this to be less than some quantity which is strictly greater than 1. So eventually this is equal to the whole space X. So we'll consider this to be case 1. So that is why we take case 1 to be the case when Rx prime is strictly greater than 1. So in this case, Vd prime x Rx prime, this is equal to all those y in x such that d prime xy, this is strictly less than Rx prime, and this Rx prime is greater than 1. We know that the distance is always less than 1. So this is equal to x because d prime xy is strictly less than 1 for every xy and x, and which is less than Rx as well. This implies y belongs to Vt prime x Rx prime for every y and x. That means this is equal to x. And since the whole space is always open in any matrix, this will be open with respect to the matrix D as well. Yeah, this implies x which is equal to Vt prime x Rx prime. Now we know that this is contained in A, that and obviously A is a subset of X, therefore X is equal to A. This implies A which is equal to X is open in XD as well. Because obviously the whole space is always closed as well as open. So the case Rx strictly greater than 1 is done. Next we move to the case. So we can take this equal greater than equal to as well. In that case also it's fine. Next is case 2, when we have Rx prime strictly less than 1. So this time I'll try to do the back calculation first. So we need to show that there exists some Rx positive such that X belongs to VDXRX, which is contained in A. That is, if we start with Y in VDXRX, we want D prime XY to be less than Rx prime. That is what we want. That is, if dxy is less than Rx, then we should get d prime xy to be strictly less than Rx. That is, now by definition, this is dxy upon 1 plus dxy. We want this to be less than Rx prime. That is, dxy strictly less than Rx prime plus Rx prime times dxy. That is 1 minus Rx prime dxy strictly less than Rx dash. Now, since Rx dash is strictly less than 1, we started with this case. So 1 minus Rx dash is positive. So I can divide it by 1 minus Rx prime. So we want dxy to be strictly less than this. And we already had dxy strictly less than Rx. So if I take Rx such that this is equal to Rx, then I will be done. That is why I will start with Rx to be Rx prime upon 1 minus Rx prime. I hope this back calculation is clear, how I started with such Rx. So let
Yes, ma'am.
okay. So let Rx is equal to this. Now this implies for any y belonging to B D X R X, we have dxy. This is strictly less than Rx, which is equal to Rx prime upon 1 minus Rx prime. From here, we are doing all those calculations again. We'll end up getting dxy upon 1 plus dxy will be strictly less than Rx prime. Multiplying both the sides by 1 minus Rx prime and eventually making the terms in this form, you'll get this. And from here, we get d prime xy strictly less than Rx prime. That is, y belongs to bd dash x Rx dash. Now, since this is contained in A, from here, this is contained in A, we get b dxrx is contained in A, and obviously x belongs to this set. Therefore, A is open in xt. And hence, both the matrices are equivalent. So can you tell me when we say that equivalent matrices are strongly equivalent?
Yes, ma'am. We can find C greater than 0 and a capital C greater than 0 such that C times dxy is less than equal to d dash xy is less than equal to capital C dxy.
For every x, y, and x. Good. So next we will see that whenever two matrices are equivalent, in that case, whenever two matrices are strongly equivalent, then in that case, directly they turns out to be equivalent. So strongly equivalent implies equivalent, not conversely. For not converse, we'll be using this example. So yeah, let's start with the first side. Next question number 6. Let xt and xt prime be two matrices on X. A and D prime be two matrices on X. Suppose they are strongly equivalent. That means there exists some alpha beta positive such that alpha times dxy is less than equal to d prime xy, which is less than equal to beta times dxy for every xy in x. Then show that d and d prime are equivalent. So equivalent means they generate the same topology. So again, we'll start with an open set. Suppose A is open in xt, then we'll show that this will be open in xt prime as well. This implies for every x in A, there exists Rx positive such that x belongs to BD XRX, which is contained in A. That means the set of all those y in x such that the distance between x and y is strictly less than Rx. This set is contained in A. Next, we need to show that we can find a ball with respect to the matrix D prime around X, which is contained in A. So again, I would like you to do the back calculation yourself. We'll take Rx prime to be equal to alpha Rx. Then for any y belonging to Bt prime, x Rx prime, we have D prime xy is strictly less than Rx prime, which is alpha times Rx. So this implies dxy, we know that we know that alpha times dxy is less than equal to d prime xy. This is strictly less than alpha Rx. So since alpha is strictly positive, it is non-zero, we can cancel this. So we get dxy to be strictly less than Rx. That means y belongs to Bt XRX, which is contained in A. So we started with y in Bt prime x Rx prime and we ended up getting y in A. That means Bt prime x Rx prime is contained in A. Therefore, A is open in XD prime. So please try the converse part. I'll come back in 2 minutes. Just try the converse part yourself.
Ma'am, is it
So, were you able to prove the converse part?
Should we take Rx to be beta prime Rx prime for the converse part?
Rx to be Rx prime by beta.
Okay, okay. Ma'am, is this proof is same as we are doing in topology, general topology? The two topology are equivalent if the basis element of one is contained in open
Yeah.
set.
It is basically the same thing.
Okay.
So all we are showing is that both have same open sets.
Yes, yes.
Hmm. Okay, so I'll leave it to you. Try yourself this converse part. Next, we will show that every equivalent matrix need not be strongly equivalent. Question number 7. Are two equivalent matrices always strongly equivalent? So you had seen earlier uh, the D prime. We proved in question number 5. Yeah, this one are equivalent. We'll show that this cannot happen for the case of strong equivalence. Question. No, because if I take, suppose X uh, D be a matrix on X and D prime XY is defined as dxy upon 1 plus dxy. We have seen earlier that D and D prime are equivalent if, let if possible, they are strongly equivalent. That is, suppose there exists some alpha beta strictly positive such that alpha times dxy less than equal to d prime xy less than equal to beta times dxy for every xy and x. So from here we get dxy is less than equal to d prime xy by alpha, and by the definition of d prime this is equal to dxy upon alpha times 1 plus dxy. And since this dxy upon 1 plus dxy is strictly less than 1, so this is strictly less than 1 by alpha. That means dxy is strictly less than 1 by alpha for every xy and x. Now suppose if we take x to be this base set of real numbers and dxy to be the usual modulus distance, this star will imply that modulus x minus y strictly less than 1 by alpha for every x, y, and x, which is not possible. No? We can make distance as large as we want, but if we take y to be equal to 0 and x to be equal to 1 by alpha plus 1, so in that case, x minus y will be 1 by alpha plus 1, which is obviously greater than 1 by alpha. We get a contradiction. Hence, equivalent matrices need not be strongly equivalent. So let's see some more examples of equivalent matrices on product space. Next. Okay. Let xd and yd prime be two matrix spaces. Show that the following matrix on x cross y are strongly equivalent. The first one is the one inspired by the usual Euclidean metric. The second one, we call it Dmax. This is maximum of dxy, sorry, dx x prime and dy y prime. The third one is d sum xy x prime y prime. This is where we sum the distances dx x prime plus dy y prime for every xy and x prime y prime in x cross. So basically we need to find some alpha beta satisfying the condition in order to show that the matrices are equivalent. So did anyone try this question?
No, ma'am.
All this is just basic calculus kind of thing, you'll see. So let's start with the fact that the x prime, this is equal to modulus of dx x prime, and I can write it as under root dx x prime square. Now this is less than equal to dxx prime square plus dy prime square, because I am eventually adding some positive term. So similarly, you'll get dy y prime is less than equal to under root dxx prime. So this is dE xy x prime y prime, and again this is also less than equal to dy y prime square, which is dE xy x prime y prime. So from here we get d sum xy x prime y prime, which is equal to dx x prime plus dy y prime. Both the terms are less than equal to dE. So this is less than equal to 2 times dE xy x prime y prime. So we got one side of the inequality. For the other side, we'll use the fact that a plus b whole square is always greater than equal to a square plus b square whenever a and b are both positive numbers. Anyways, this is always positive. The terms are negative. No, this happens for AB positive. So this implies if I replace A by dx prime and B by dy prime whole square, this is greater than equal to dx prime square plus dy prime square. Taking under root both the sides, and since everything is positive, everything is well defined. So from here we get d sum xy x prime y prime, which is equal to dx x prime plus dy y prime. This is greater than equal to under root dx x prime square plus dy y prime square, which is equal to dE xy x prime y prime. So from here we get the other side of the inequality. So therefore dE xy x prime y prime, this is less than equal to d sum xy x prime y prime, and this is from first, this is less than equal to 2 times dE xy x prime y prime. So therefore our in this case our alpha is 1 and beta is 2. Hence dE and d sum are strongly equal, because this happens for every x, y, and x prime, y prime, and x cross y. Okay. Next, we will prove equivalence between d sum and d max, and eventually all the three of them are strongly equivalent. Now, we have d max xy x prime y prime. This is equal to maximum of dx x prime dy y prime. This can be either dx x prime or dy y prime. Obviously, either one of them will be greater than the other one. So eventually this will be less than equal to, if this is equal to dx x prime, this is less than equal to dx x prime plus dy y prime, because dy y prime is positive. And if this is dy y prime, then again it is less than equal to dy y prime plus dx x prime, because that's a positive term. So eventually I can write it as dx x prime plus dy y prime. And this is equal to p o. So everywhere with y, I had to use the matrix on y. This is d prime. This is d prime. Yeah, this is d prime, d prime, d prime, d prime, d prime. Okay, so this is d sum xy x prime y prime. So we got one side of the inequality, and for the other one we have d sum xy x prime y prime. This is equal to dx x prime is d prime by y prime. This is less than equal to, now this term is less than equal to maximum of both the terms. This term is also less than equal to maximum of both the terms. So I can write it less than equal to maximum dx x prime d prime by y prime plus maximum dx x prime d prime by y prime. Now this is equal to 2 times d max dx x prime d prime by y prime. So and this is d max of xy x prime y prime. So therefore, from here we get d max xy x prime y prime is less than equal to d sum xy x prime y prime, which is less than equal to 2 times d max oh 2 times d max xy x prime y prime. Therefore, d max and d sum are equivalent, and hence all three matrices are strongly equivalent. Hence we are done. I hope this proof was fine. This was all just basic calculus things.
Ma'am, DE and D max, how they are strong equivalent then?
Using these two conditions, you can get the relation between D and D max as well.
Okay.
Because see, D is less than equal to D sum, and D sum is less than equal to 2 times D max. So from there you get Okay, so I'll stop here. We'll continue in next class. So you want me to prove that inequality na, for if L and M are two linear operators, then what about the composition? I'll start with that problem in the
Ma'am,
next.
there is one thing also.
Hmm.
For the set of all bounded real valued function on a metric space X, the
Hmm.
to show that supremum of mod of fx is the norm for that set. How can you show that? And also there is inequality here also. Norm of two function is less than equal to product of their individual norm.
So are you talking about this exercise 10.20 in the detailed notes?
Oh, I think that would be
The composition one is exercise 10.21
okay.
and other what the norm part. Are you asking about that equivalent norm on the equivalent operator norm?
Sup norm, ma'am.
Okay, soup norm.
On the set of bounded function from x to r.
So you need to show that this is
This is a norm and
okay. Okay,
product.
see, okay, okay. This is example. This is an example, na? Example 10.13.
Yes, yes. In lecture, in example 5, uh, that
So
given
you
exercise.
want to prove that the soup norm is actually a norm.
Yes, and the inequality that norm of composition of two function is less than equal to product of the individual norm.
Okay, okay. Okay, I'll do that in next class.
Okay, thank you.
Okay, then we'll meet next Sunday.